So today, lots of things, complicated derivatives and implicit differentiation and all sorts of fun stuff. Let's start with something kind of complicated. Let's say we have the following. Our function was f of x equal to the square root of 3x divided by x squared plus 1 all to the 5th power. Now we'll take the derivative of that. Well, I would say there's one small thing you can do to make your life a little bit easier before you differentiate this. Specifically, this square root of 3x here, I would really much rather write that as the square root of 3, the square root of 3 times the square root of x, all over x squared plus 1 to the 5th. And then I'd really rather think of that as just the square root of 3 times x to the 1/2, all over x squared plus 1 to the 5th. So that now when I take the derivative, the square root of 3 is just a constant that's going to hang out when I deal with it. So taking the derivative, we have a bunch of stuff raised to the 5th power. The derivative of x to the 5th is 5x to the 4th. The derivative of stuff to the 5th is 5 times your stuff to the 4th. And then we're going to multiply by the derivative of that stuff. We still have the square root of 3 times x to the 1/2 over x squared plus 1. Now we're going to multiply by the derivative of all this inside stuff using the quotient rule. It's going to be the bottom x squared plus 1 times the derivative of the top. So the derivative of the top, the square root of 3 is a constant that's going to hang out. And the derivative of x to the 1/2 is going to be 1/2 x to the negative 1/2. Subtract and switch it up. Now instead of the bottom times the derivative of the top, it's the top times the derivative of the bottom. So you're going to have the square root of 3 times x to the 1/2 times the derivative of x squared plus 1, which is 2x. All divided by the denominator squared. So it's pretty term. Yeah. No, I don't even want to go there. That brings us something interesting. Let's do a similar problem that we will simplify. So sometime, there's gonna be enough room there, sure, that's fine. So we want to find where g of x equal to 3x plus 6 over x squared plus 2. X squared plus 2. I'm blowing it. That's not what I wanted at all. Sorry, let's scratch that. Apologies. Sometimes you make up something and you realize that's not going to work out. Let's try the following. Plus, I was going to run out of room there anyway. Find where g of x equal to 3x plus 6 over x plus 1 to the 4th has horizontal tangent lines. Sorry, you can't see that. Apologies. So what does it mean when we say we want to find where a function has horizontal tangent lines? Well, a tangent line has what kind of slope? Right, 0. So you're really just finding where the derivative is equal to 0. So it's kind of a lot of words. And again, it's something we will do in chapter 4 when we start finding maximum and minimum values. For now, it's kind of just like, oh yeah, it's another way of asking this question. So we're going to take our derivative, which is going to be the bottom times the derivative of the top, which is 3, minus the top, times the derivative of the bottom, which is 4, times our stuff, the 3rd power, times the derivative of the stuff, which in this case is just 1, all divided by the denominator squared. And x plus 1 to the 4th squared is x plus 1 to the 8th. Now, I really don't want to multiply at the top, because it's just going to be a pain, right? X plus 1 to the 4th is a pain. So is x plus 1 cubed. But I have to do something to be able to set this thing equal to 0 and solve it. And the thing is, with quotient rules like this, where you're starting off with something in the denominator that's raised to a higher power, there's often some level of simplification you can do before you are trying to set this equal to 0. Specifically, I can factor out an x plus 1 to the third from the numerator. So if I factor out an x plus 1 to the third, look what I've got. Still have the same denominator, x plus 1 to the 8th. But here, when I factor out an x plus 1 cubed, I'm left with an x plus 1 times 3. Oh my gosh, did I pick a stupid number? I really did. Sorry. I'm just seeing what's going to happen here. And well, sometimes this happens. It's fine. Minus, oh no, it's going to be fine. I forgot about the 4. Sorry, I'm getting all caught up in this. So I factor out an x plus 1 cubed, left with an x plus 1 times 3, minus a 3x plus 6 times 4, and that's it. And now the x plus 1 cubed and the x plus 1 to the 8th, I can cancel the x plus 1 to the third power and be left with whatever's in the brackets here over x plus 1 to the 5th. We should simplify what's in the brackets here. So distributing the 3, we get 3x plus 3 minus distributing the 4, we get 12x. And be careful here, minus 24. And simplifying it one step further, we have 3x minus 12x is negative 9x. 3 minus 24 is negative 21 all over x plus 1 to the 5th. And now that's much, much easier to set equal to 0 and solve for x. So we're only going to get one solution here. If we set this whole thing equal to 0, we can multiply both sides by the denominator. So that negative 9x minus 21 equals 0 times anything is 0. Solving for x, we get negative 9x equal to positive 21, or x equal to negative 21 over 9, which reduces to negative 7 over 3. X equal to negative 1 would not be a solution here. X equal to negative 1 is a value that would make this derivative undefined. Because it's not in the domain of the original function. Something else worth noting here is that when you take a derivative of something, some quotient, and the bottom is raised to a power, if you take the derivative and simplify it enough, you should get to a point where the new power in the denominator is exactly 1 bigger than the previous power. So this power was 4 here, and I simplified and got to an x plus 1 to the 5th in the denominator. That's not a coincidence. So I will tell you, in fact, we could, yeah, maybe. If we took the derivative of this, negative 9x minus 21 over x plus 1 to the 5th, I should say, if we took the second derivative of g of x, then we would, after simplification, end up with x plus 1 to the 6th power in the denominator. Always happens. In fact, let's go ahead and do it. It's not that terrible. Sometimes it's terrible. So I'll point out, it would be extremely terrible to take the second derivative if we were starting with this. Taking the derivative of that unsimplified is going to be really awful. But if you simplify it down to here, although it's not going to be fun, it's going to be much, much better than if we had started with that. So it's almost always worth your while to simplify an expression before taking its derivative. Thank you. So let's go ahead and find g double prime. No, let's not try and squeeze it in there. It's a real design. So we're taking the derivative of g prime. Sorry, I keep quizzing that. The same idea. It's going to be the bottom, x plus 1 to the 5th, times the derivative of the top, which is negative 9, minus the top, which is negative 9x minus 21, times the derivative of the bottom, which is 5 times x plus 1 to the 4th. I'm still thinking about the chain rule here, even though I'm only going to multiply by the derivative of the inside, which is 1 here. But whenever my stuff is not just x, I should always at least think of, oh yeah, I have to multiply by the derivative of the stuff. In this case, it's just 1, so we don't need to write that down. And then we're going to divide by x plus 1 to the 5th squared, which is x plus 1 to the 10th. All right, so looking at that expression, all right, show me on your fingers, what's the power of x plus 1 I can factor out from the top? It's either this many or this many. It's always going to be the lesser number. So it's going to be 4. In fact, even if the lesser number is a negative number, like if you have an x plus 1 to the negative second and an x plus 1 to the negative third, you can factor out the lesser number, which is x plus 1 to the negative third. Because negative 3 is lower, it's lefter, more left than negative 2. So here we're going to factor out an x plus 1 to the fourth. And on top, we're left with an x plus 1 times negative 9 minus a negative 9x minus 21 times 5. No x plus 1's there. All divided by x plus 1 to the 10th. And hey, look what's going to happen. 4 of those are going to cancel out with 4 of those. And we're exactly left with an x plus 1 to the 6th on the bottom as predicted. So this is just something I've noticed. It's not super important, but you should know that if you're simplifying a quotient like this, eventually you should get down to just a new power that's 1 larger than the previous power you had. And then we could simplify the top, I guess. It's negative 9x minus 9. Minus 5 times minus 9 is plus 45x. And minus 5 times minus 21 is plus 105. All over x plus 1 to the 6th. And so if we simplify one last step, we get 36x. 105 minus 9 is 96. All over x plus 1 to the 6th. And if you want to set this one equal to 0, you'd find x equal to negative 96 over 36, whatever that happens to be. Yeah. So I will say, this is something we will do when we start talking about graphing things and finding relative maxima or minima or inflection points or intervals of increasing or decreasing or concavity. So this is definitely not just doing it for the sake of doing it, right? There is something to be done with this later on. All right. Let's look at more things. Let's look at some more. People, a lot of people ask for more complicated derivatives, so I'm trying to give you what you want. Let's look at something like this. Oh yeah, where'd that one go?
James?
Yes.
I have a question.
Sure.
Why do we not concern the numerator? Is it, or the denominator when we're looking at, we're only looking at the 36x plus 96, but not looking at the x plus 1 to 6.
Sure. Why am I not asking about setting the denominator equal to 0?
Yeah.
So if you look back at the original function, which was 3x plus 6 over x plus 1 to the 4th, I'll point out that this original function, if we were to start graphing this, in fact, we might as well graph it. We've done all the important things. So if we're going to graph this, I'd point out that you would have an x-intercept. In fact, why am I just saying it? Let's draw it out. So here's a preview of what's coming up in chapter 4, graphing some terrible stuff. So if I look at g of x equal to 3x plus 6 over x plus 1 to the 4th, I'll point out that we have a y-intercept. We set x equal to 0. We're going to get g of 0 equal to 6 over 1. How convenient. Just 6. X-intercept. Set the whole thing equal to 0. But when we set a fraction equal to 0, we only end up setting the numerator equal to 0 because you multiply both sides by x plus 1 to the 4th. I have to grab a red pen. You multiply both sides by the denominator. The left-hand side of the denominators cancel, and you just get 3x plus 6. On the right-hand side, 0 times anything is still 0. So here we end up getting 3x equal to negative 6, or x equal to negative 2. Where x-intercept would be negative 2 comma 0. And then there's 2 more things we typically look for if we're not using all the derivative information that we just found. We look for vertical asymptotes. And you get vertical asymptotes by setting the denominator equal to 0, which is kind of the answer to your question. So the whole deal here is if you set x plus 1 to the 4th equal to 0, you're going to get x equal to negative 1. That's a vertical asymptote. The function isn't defined there, so we can't really think about x equaling negative 1. Or we can, but there's no like good answer to the question, what happens when x equals negative 1? The function is undefined at that point. And then I guess we could also think about horizontal asymptotes. I know it's been a little while, but we all did definitely talk about taking limits of things like this as x goes to infinity back in the beginning of the quarter. So if I take the limit as x goes to infinity of 3x plus 6 over x plus 1 to the 4th, what should I get? Ooh, what's the degree on top? What's the degree on the bottom? So since the top has a lower degree, the limit ends up being 0. The bottom is getting much larger than the top. So if we try to graph this, here's what we've got. We've got a y-intercept of 6, an x-intercept of -2, a vertical asymptote of -1, that's annoying. And then a horizontal asymptote of 0. So the graph probably looks something like this. Again, it's not going to be perfect, but it's going to come down like that. And it's probably going to be something like this. Get that x-intercept and then turn around somewhere like that. Oh yeah, but now yes, we can do something kind of cool. Is that we can look back at our first derivative stuff and notice that for our first derivative, which was this equation here, we have a horizontal tangent line. Right, that's what the question was. Where do we have horizontal tangents? We got that by setting the derivative equal to 0. We got -7/3. So here's -1, here's -2, here's -7/3. And right there, at x equal to -7/3, y equal to something terrible, we have a horizontal asymptote. Horizontal tangent line. Oh, sorry, terrible. So the idea moving to the, again, this is kind of a little bit beyond where we're at, but we kind of got on this track, is that we're going to be able to find where a function has a relative minimum, right? It bottoms out there, or a relative maximum by finding where the derivative is equal to 0, because that's where you're going to have a horizontal tangent line. Back to your question, why am I not looking at where the denominator equals 0? Well, if I set the denominator equal to 0, I'm just going to end up getting x equal to -1. And if you look at this graph here, at x equals -1, that's where we have this vertical asymptote where you can't have kind of anything other than just the vertical asymptote you've already got. So once you've got a vertical asymptote for a function, it can't be anything else. You're kind of just stuck with it. Okay. Sorry, I got off on a little bit of a tangent there. Let's get back to some, I wrote something down, now I can't see. Oh, there it is. Haha. Okay. Let's say we want to find the first and second derivative of f of x equal to cosine cubed of 3x squared plus 7. So how do we deal with the power of a trig function? I personally recommend rewriting it. I would write this as f of x equal to cosine of 3x squared plus 7, all raised to the power of 3. So that then we can think of using the chain rule. Again, it's the usual chain rule stuff, right? I've got some stuff cubed. My derivative is going to be 3 times my stuff squared times the derivative of that stuff. It's going to be 3 times cosine of 3x squared plus 7. And then we have to multiply by the derivative of cosine of 3x squared plus 7. Well, the derivative of cosine of x is negative sine of x. So the derivative of cosine of some new stuff is going to be negative sine of that new stuff times the derivative of that new stuff. That's going to be negative sine of 3x squared plus 7 times the derivative of the 3x squared plus 7, which is 6x. Kind of a bit funky, right? There's a chain rule and a chain rule there. So let me have you all try a different one. Oh, I said second derivative. Oh, second derivative, James. Ooh, James, how could you? Do I really? Wow, I said it. Okay, so we're going to kind of regret this probably, but we'll do it anyway. So before I do the second derivative, I should definitely take a minute to simplify this. There's not a lot of simplifying to do, but there's a little. The negative, the 6x and the 3, I would combine into a negative 18x times cosine of x squared plus 7. Sorry, cosine of 3x squared plus 7 squared times sine of 3x squared plus 7. Yeesh. Regrets. Oh well. So I'm going to think of using, unfortunately, the triple product rule here. where we have this times this times this. And as a reminder, I know we didn't spend a whole lot of time talking about the triple product rule, but for a product of any number of things larger than 2, it's just the derivative of one piece times the other piece is left alone. And you get each piece having its own derivative. So each of these 3 pieces, each of their derivatives is going to show up once. So I'm thinking of this as like an G times an H times a J. Then my triple product rule is going to be G prime times H times J plus G times H prime times J plus G times H times J prime. And each derivative gets to happen once, and it's multiplied by the not derivatives of all the other pieces. So for F double prime, got a little too excited with the second derivative here. The derivative of G is going to be negative 18, and then we're going to multiply it by the other 2 pieces left alone. It's kind of terrible to write out. Cosine of 3x squared plus 7 squared times sine of 3x squared plus 7. Plus, so, and again, I guess I should go ahead and write the notation here. All right, so there's my G prime times H times J. Now we're going to do G, which is just negative 18x, times the derivative of H, which is going to be the worst one. So the derivative of cosine of some stuff squared, ooh, it's going to be real messy. It's going to be 2 times, I should say, derivative of some stuff squared is 2 times our stuff to the first times the derivative of cosine of 3x squared plus 7, which is negative sine of 3x squared plus 7, times the derivative of the inside stuff here, which is 6x, times the j over here, which is, good lord, sorry, it's a little messy. So I'll just point out, there's my G, there's my H prime, and there's my J. Finally, the last part here, G times H times J prime, so negative 18x times this cosine of 3x squared plus 7 squared times the derivative of J. So the derivative of sine of some stuff is going to be cosine of the stuff times the derivative of the inside stuff. Wow, it's pretty gross. Like even like really gross. I'm not gonna lie. So I would say the thing to see here is really that we just have to take it step by step, right? Like there's a lot of things going on, but if you just kind of deal with one piece at a time, not too terrible. I'm going to give you all one that's much less terrible to try on your own. So I'll try taking for f of x equal to, let's say, let's go tangent to the fourth of x. I want you to find the first derivative. And I would recommend rewriting this as tangent of x to the fourth power. Find that first derivative there. So our function, I'm not finished with the derivative there. Our function is something to the fourth power. The derivative is 4 times our something to the third power, and then we have to multiply by the derivative of the something. And the derivative of tangent of x is secant squared of x. All right. Now what? Now you're going to find the second derivative. And now find the second derivative. And there isn't really a lot of rewriting to do here. If I was going to rewrite this, I actually, the only thing I would really do to rewrite this is write it as 4 times tangent of x cubed times secant of x squared. And I would point out that the 4 is just going to hang out. So 4 times, got some product rule and some chain rule to deal with there. Take a look here and see what we should be getting. So the 4 hangs out. The derivative of some stuff cubed is 3 times my stuff squared times the derivative of the stuff, the derivative tangent again, secant squared x. And then we're just leaving the secant squared x over here alone. Sorry, it's a little messy there. And then switch it up. We leave the g alone. So we leave tangent of x cubed alone. Sorry, tangent of x quantity cubed or tangent cubed of x. And then the derivative of secant squared is going to be 2 times r secant to the first power times the derivative of secant, which is secant of x times tangent of x. Which is a bit messy. Normally, I wouldn't bother simplifying anything like this, but I think here we can make an exception because if you simplify it, it does get a little bit nicer. I probably distribute the 4, say 4 times 3 is 12, and 4 times 2 is 8. I'm gonna have 12 times tangent squared of x, and secant squared times secant squared is secant to the 4th. Plus, same deal here, the 4 times 2 was 8. Tangent cubed times tangent of x is tangent to the 4th. And then secant times secant is secant squared. So you can make this look at least a little bit less terrible. There's probably even some weird factor you could do and some trig identities you could use to make it look even less terrible, but that's not really the point. Questions about this one? Yeah. Oh, you could, so here, the reason so you're right, I could have, if I wanted to, said, I could have included the 4 in each of these, instead it was, instead of having it here, I could have said it was 4 times 3, which would have been 12 times tangent squared, and then also, but the 4 would have also been over here too, and then I would have had a 4 here times tangent cubed, and then times 2. Still giving me a 12 here and an 8 here. Yeah, when I have, it depends. Sometimes when I have a product with a constant in front, sometimes I like to group that constant with the first function, but here I did not. Here I just kind of pulled it out in front. Said the constant's gonna live out here, and we're gonna take the derivative of all the stuff and just then maybe distribute it through later on. Cool. Let's look at some implicit differentiation. Oh yeah, question, sorry. Okay. Let's look at some implicit differentiation and then some related rates. So let's look at the following thing. Let's say we want to find dy dx for, yeah, this is gnarly. 3x squared y to the 5th plus 6 to the 4th power equal to 2x plus 1 over root y plus the natural log of x times y. And I would do one thing before I started just differentiating away here. I would rewrite the right-hand side. So I'm going to rewrite this whole thing as 3x squared y to the 5th plus 6 to the 4th. This is going to be gross. This is a problem. This is a variation of a problem someone sent me. Equal to 2x plus, let's rewrite this as y to the negative 1/2. And it's almost always a good idea when you're differentiating a logarithm to break it up using the rules of logs. So instead of natural log of x times y, I would much rather write this as the natural log of x plus the natural log of y. It's going to be less work to take the derivative of that in the next step. Okay, so now we're going to differentiate. I'm going to remind everybody that when you're doing implicit differentiation and you're taking the derivative of both sides, we are always under the assumption that y is a function of x. Meaning, essentially, we're doing the chain rule, and y is always acting like our stuff. So when you see y cubed, you should really say to yourself, I have some stuff cubed. All right, so starting with the left-hand side, oh my goodness. We have a whole bunch of stuff to the 4th power. And just like the derivative of tangent to the 4th was 4 times tangent cubed times the derivative of tangent, the derivative of all this stuff to the 4th power is going to be 4 times all that stuff to the 3rd power times the derivative of the inside stuff. Okay, the 6 is not going to be of consequence when we take the derivative, because the derivative of a constant on its own is 0. But the derivative of 3x squared times y to the 5th, we're going to have to use the product rule. So it's going to be the derivative of 3x squared, which is 6x, times y to the 5th left alone, plus, switch it up, leave the 3x squared alone, and then the derivative of y to the 5th, it's really some stuff to the 5th. And the derivative of some stuff to the 5th is 5 times our stuff to the 4th times the derivative of our stuff. And I wrote y prime, which is fine, instead of dy dx. So all of this here, all of that is the derivative of 3x squared y to the 5th plus 6. Four times our stuff cubed times the derivative of our stuff. Let's move over to the right-hand side. It's going to be less terrible. The derivative of 2x is 2. The derivative of y to the negative 1/2, or some stuff to the negative 1/2, is going to be negative 1/2 times our stuff to the negative 3/2 times the derivative of our stuff. Yeah. Because when we take the derivative using the power rule, we bring down the power, and then our new power is 1 less. And negative 1/2 minus 1 is negative 1/2 minus 2 over 2. And negative 1 minus 2 is minus 3 over 2. And then the derivative of the natural log of x is 1 over x. The derivative of the natural log of y is 1 over our stuff times the derivative of our stuff. So 1 over y times y prime. I will point out, breaking up the natural log of xy as the natural log of x plus natural log of y was a good call. Right? If we had taken the derivative of the natural log of xy, it would have been 1 over xy times the derivative of xy, which would have required the product rule, which would have been 1 times y plus x times y prime. Dealing with this 1 over x plus 1 over y times y prime is much nicer than dealing with that. I can't say it enough. If you have the opportunity to simplify before you take a derivative, you should. I will say it all the time, though, but I still can't say it enough. Okay, so now we've done the derivative, oh my gosh, words. We've done the calculus part, taking the derivative. The rest is the terrible algebra part. We have to solve for y prime. So this one requires an extra algebra step because you've got a y prime stuck inside a bracket that's being multiplied by some other stuff. So we have to distribute this 4 times 3x squared y to the fifth plus 6 cubed to each of these two terms here. And distribute it here and here. And then we're going to have to collect all the y primes on one side, everything else on the other side, factor out y prime, divide by what's left. It's going to be really awful. Let's do it. So, yeah, dude, oh my gosh. Okay, it's really terrible. Well, let's do it. So when I multiply this by this, the 4 times 6 is going to be 24, and I will make that simplification. But then it's going to be 3x squared y to the fifth plus 6 to the third times x times y to the fifth plus, and then 4 times 3 is 12. So 12 times 3x squared y to the fifth plus 6 to the third times x squared times 5. I forgot the 5 there. Oh well, we'll get to the next one. X squared times 5 y to the fourth times y prime equal to the same stuff over here. 2 minus, no, I won't. 1/2 y to the negative 3/2 times y prime plus 1 over x plus 1 over y prime. Goodness gracious. Okay. Here and here and here are all the terms that have a y prime. So all those terms have to go on one side, all the other terms have to go on the other side. Okay, I'm gonna ask for permission to do one thing. Well, I'm not gonna ask, I'm gonna tell you I'm gonna do one thing that I wouldn't normally do. Instead of bringing all the y primes to one side and then factoring out a y prime, I'm gonna do those two steps in one step, so it's not all the writing in the world. So I'm gonna bring all my y primes to the left. So this term, this term, and this term, so I'll have this plus 1/2 y to the negative 3/2 times y prime minus 1 over y prime. And I'm also going to factor out a y prime at the same time. So I'm going to get y prime times this term without the y prime. So 12 times 5 is 60. So 60 times 3x squared y to the fifth plus 6 cubed times x squared times y to the fourth plus, because I'm bringing it over here, 1/2 times y to the negative 3/2. The y prime got factored out. Minus 1 over y equal to the other stuff. So I've got a 2 plus a 1 over x. And then I've got this term over here, which is going to become negative. It's minus 24 times 3x squared y to the fifth plus 6 cubed times x times y to the fifth. Wow. Might be the worst problem I've ever seen. That's not true. Might be the worst implicit differentiation problem I've ever seen. Finally, divide both sides by this giant mess here to get y prime equal to all of that. 2 plus 1 over x minus 24 times 3x squared y to the fifth plus 6 to the third power times x times y to the fifth over all of that. 60 times 3x squared y to the fifth plus 6 to the third times x squared y to the fourth plus 1/2 y to the negative 3/2 minus 1 over y. And then cry. Okay. Yeah, pretty heinous in the world of implicit differentiation. But the process, even though it was heinous, the process is still the same thing we've done every time with implicit, right? You get your equation, maybe you simplify it a little bit, take the derivative of both sides, distribute if you have to, bring all the y primes to one side, factor out the y prime, divide by what's left over. That's always the same, like 4 or 5 steps. Let's see. What time? Okay, we got, yeah, we got time. Okay. Yeah, let's go ahead and continue on. I feel like I had one other one here that looked good. No. Okay. So let's look at something that feels very related. Well, okay, fine. You'll get the joke in a minute, or you won't, or you got it already and you didn't think it was funny, which is also fine. Okay. So let's look at the following. Given dy dt, sure. Nope, that's not what I wanted, but fine. Given dy dt is equal to 5 inches per second, and the f of y is equal to y cubed times sine of y all to the fourth power. Find df dt when y is equal to pi. So this question is not phrased that atypically. It's not the best phrasing ever, but I wouldn't be surprised if you saw something kind of like this in the future at some point. Basically, we're saying we're giving you how something's changing. I'm telling you how, actually, what am I telling you? When I say given dy dt is equal to 5 inches per second, I'm telling you how what thing is changing, how y is changing, right? We're being told that y is increasing as time goes on at 5 inches per second. And I'm asking you to find how the function f is increasing when y happens to be pi, I should have said pi inches, really. So we're going to take the derivative here. And really, I could have just written this left side as just f. So we're going to differentiate. Wow, spelling, challenging. Both sides with respect to time. So we're definitely doing related rates here, but we've kind of skipped the typical first couple steps where we have to like draw a picture and set up the relationship. They've already given us the relationship and just asked us to kind of go straight ahead. All right, so on the left-hand side, the derivative of f is just going to be the derivative of f with respect to time, df dt. On the right side, that's where we're going to have to use our differentiation skills. Say, okay, well, I have a question, actually. We have a choice. You could choose to take the derivative of this as is, which would be fine. You've got some stuff to the fourth. It's going to be 4 times your stuff cubed, and then the derivative of the inside stuff is going to have to use the product rule. Or, and I feel like it might be the better choice, actually, you could rewrite this by raising each factor to the fourth power and writing this as y to the 12th times sine of y to the fourth. It's probably not a lot better that way, but it's probably a little better. So yeah, let's go ahead and think of it as this, where we're just going to directly apply the product rule first instead of the chain rule first. Okay, so product rule, the derivative of y to the 12th is going to be 12 times y to the 11th times the derivative of y. Because again, y is acting like some stuff. We know that y is a function of t. They told us right here, dy dt equals 5 inches per second. If the derivative of y with respect to t is a thing, that means that y is a function of t. Times the other thing left alone, plus switch it up. Y to the 12th gets left alone, and then we're going to multiply by the derivative of sine of some stuff to the fourth, which is 4 times sine of y cubed, times the derivative of sine of y, and the derivative sine of some stuff is going to be cosine of the stuff, times the derivative of the stuff. And this is where my answer is probably going to be very unexciting, which is fine. Okay. Something to be careful about here. They're not actually asking us to solve for anything. Well, that's not true. But normally, if you saw a question like this, if you weren't really thinking about it, you might just start trying to solve for dy dt. That feels like a very natural thing to do. That's not at all what they want us to do. First of all, we're trying to find df dt, not dy dt. Second of all, they told us what dy dt was. They told us that dy dt was 5 inches per second, and they're asking us to find df dt when y is equal to pi. So we're just going to plug in all the things we know. And that's typically the case. After you take the derivative of both sides of your related rates situation, then you just plug in what you know, solve for what you don't. All right, let's do it. So Yeah, I'll do the work. So plugging in, we're gonna get 12 times pi to the 11th power times dy dt, which is 5. I don't like to write the units until the very end. Also, the units here probably wouldn't make a whole lot of sense because I got ridiculous powers. Times what's sine of pi? 0. Maybe I should have looked at that first, because 0 to the 4th is 0, and 0 times anything is 0. Plus, over here, pi to the 12th times 4 times up, sine of pi, which is 0 again, times cosine of pi times dy dt. So this one, because of lack of foresight, ends up being just a good old 0. Sometimes that happens. Sometimes you plug in a bunch of stuff and you just get zeros all the way. So here, because of the particular moment, so what's kind of interesting here is if you think about it, you've actually kind of found a maximum or a minimum of this function, because this function df dt is essentially you've gotten to a place where it's no longer increasing or decreasing. Its rate of change at this particular moment happens to be 0, probably feet per second. The units here are a little wonky, I'm not gonna lie. So that's one example of kind of a weird related rate problem. Here's another one, which is a little less weird, but still a little bit weird. Yeah, we got time. We got time. Okay. Let's look at this next example. Where'd you go here? Yeah. Sorry. I see that. Suppose you have the following situation. Suppose that the edges X, Y, and Z of a box are initially X equal to 2 inches, Y equal to 1 inch, and Z equal to 6 inches. We also are told the following: the box is changing shape. The sides change in the following ways. Yeah. We're told that, so I can do the right words or right derivatives. They're telling us that X is increasing at 2 inches per second. So we should write down that dx dt is equal to 2 inches per second. And all we're saying there is X is increasing at 2 inches per second. Similarly, we're told that Y is increasing at 3 inches per second. Dy dt equals 3 inches per second. And we're told that Z is decreasing at 1 inch per second. So dz dt is going to equal -1 inches per second. And then we're asked to find the following. So after 3 seconds have elapsed, how is the volume changing? Okay, well, you probably don't have to draw a picture, but it probably doesn't hurt to draw a picture. So here's a picture, sure, like. So here's like my Z, here's my X, here's my Y. Now I want to find how the volume is changing. I want to know how to find what dV dt is, the rate of change of the volume. Typically, once you've identified what you know is changing, in this case, X, Y, and Z, and what you're trying to find out is changing, volume, then you want to get an equation relating those variables. And here, it's usually just a geometry formula, like volume, area, Pythagorean theorem, similar triangles, I don't know, other things maybe, but those are the pretty commonly, it's the volume of your shape, the area or surface area of your shape, maybe the perimeter or circumference of your shape, or maybe the Pythagorean theorem. Like it's kind of one of those things typically if it's some sort of geometry thing. In this case, you're going to have that volume is equal to X times Y times Z. Most of the time, most is probably too hard. A lot of the time for related rates problems, we then want to try to get your thing in terms of one variable. Like usually having x and y and z would be a problem, but not here because we've been told how x, y, and z are all changing. So we're just going to take the derivative of both sides. So now we're going to differentiate. The derivative of volume, oh, I should say, with respect to time. Almost always time. Not always, though. Okay, so we're differentiating. The derivative of volume is dv dt. And for the derivative of x times y times z, this triple product, we have to use the triple product rule. So it's going to be dx dt times y times z plus x times dy dt times z plus x times y times dz dt. Each derivative shows up once, and every time you have a derivative, it's multiplied by all the other not derivatives. That's a generally applicable rule, right? If it was 4 things, it'd be 4 pieces, and each piece would have 1 derivative multiplied by the other 3 not derivatives. Yeah, Monty, what's up? No, I could have written it as like dx dt times y times z plus dy dt times x times z plus dz dt times x times y. It doesn't matter how I write those products. I'm just writing it in a way so that x, y, z is always in the same order, but it doesn't really matter. Okay, we've taken the derivative of both sides. Now the next step is always to typically plug in the things you know, solve for what you want to know. So here we're going to plug in basically everything on the right-hand side of this equation. So we're going to get that dv dt is going to equal, so dx dt is 2 inches per second, y is 1 inch, z is 6 inches, x is 2 inches, dy dt is 3 inches per second, z is 6 inches, and finally x is 2 inches, y is 1 inch, and dz dt is negative 1 inches per second. Now I know I didn't write any units, but I want to point out that each of these 3 different things added together are in inches per second times an inch times an inch. That's going to be inches, 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 so inches cubed per second, which are the units we would expect for how a volume is changing. So we're going to get 12 plus 36 minus 2, that's going to be 46 cubic inches per second. So at that moment in time, that's how fast the volume of the box is increasing. At a different moment in time, it would be a different value. So just something to be aware of. Yeah. Interesting. I think I made an error. Because there was something I forgot to include here. The question was, after 3 seconds have elapsed, how are things changing? So this would have been the correct answer if the question had been, how are things changing after 0 seconds have elapsed? Because when time is 0, that's when x, y, and z are respectively 2, 1, and 6 inches. But 3 seconds later, well, if 3 seconds have been going on and dx dt is 2 inches per second, oh, we can't see that, sorry. So at time equals 0, we have that x equals 2 inches, y equals 1 inch, and z equals 6 inches. But 3 seconds later, x is increasing at 2 inches per second, so x is increased by 6 inches. So x should now be 8 inches. Y has been increasing at 3 inches per second for 3 seconds, so y should now be 10 inches. And z has been decreasing by 1 inch for every second, so z should now be 3 inches. That's going to be a very different answer. So instead, I should be getting that, sorry, you can't see all the things, apologies. So we should really be getting that dv dt is equal to, so dx dt is still the same, it's still 2, but now y and z are 10 and 3 respectively. And now x is 2, x is 8, goodness gracious, James. dy dt is still 3, and z is 3. And finally, our x times y is going to be 8 times 10, and dz dt is still negative 1. Okay, let's actually get the correct answer here. So here we're going to get 2 times 10 times 3 is 60. 8 times 3 times 3 is 8 times 9, which is 72. And 8 times 10 times -1 is -80. So we really have -20 plus 72, which is 52 inches cubed per second. It's really important to make sure we pay attention to the whole question, right? It's easy to miss that fact. Cool. I've been a little too much here. So I would classify these as kind of some off the beaten path related rates questions, right? These are less typical in my opinion. Let's look at a more typical example. Let's see, where'd you go here? Yes. Oh, we that both there. So here's a typical example. Sure. Julian is flying a kite at a constant height of 40 feet in the air. Which just I'll say seems really gonna be a pretty hard feat to imagine, right? Making sure your kite was always 40 feet above the ground, like this seems maybe really hard. Not the point though. The wind is pushing the kite horizontally away from Julian at a speed of what do we got here? 10 feet per second. At the moment, the kite is 50 feet away from Julian. And we'll talk about that more in a second. How fast is the kite? All right, sure, moving. There's a better way to say this. I was gonna write how fast is the kite moving away from Julian, but a better way to kind of get at that meaning is how fast is Julian letting out the string? So many words. Let's draw a picture. Here's Julian. And here's the kite he's flying. And the kite is always staying at this height above the ground. If we're thinking of this, like if we're thinking of this being the ground, then this height here is always 40 feet. No matter if the kite's here or later on when it gets pushed away, like over here, or the kite's here, that will still be at a height of 40 feet. So you can kind of see from the picture here that, oh yeah, as time goes on, he's going to have to let out more string, right? Because the distance from to the kite is getting longer and longer. So here's what we have in our original picture, which I've kind of now destroyed. Let me just draw this triangle again. This height here is 40 feet. It's not changing. But this length of string certainly is getting longer. And this horizontal distance to the kite is also changing. So there's our kind of setup for labeling the sides of the triangle with variables for things that are changing and constants for things that are staying constant. And now we should also talk about what we know is changing. So we are told that we know how the horizontal rate of change or speed of the kite is, right? The kite is moving, getting pushed that way at a speed of what, 10 feet per second, I think it was? Yeah. So we know that dx dt is equal to 10 feet per second. And we're asked to find the rate of change of how fast the string is letting out. We want to know what ds dt is equal to. And then we typically do the thing where we find an equation relating those variables. In this case, it is going to be the Pythagorean theorem. So we're going to say that x squared plus 40 squared equals s squared. I should say, I know I've said this before, but when we talk about relating the variables, it's really we're relating all the not time variables. Right? You never think about time being there, because when you take the derivative of both sides, that's when time kind of enters the whole fray. So now we're going to differentiate both sides with respect to time. So be careful here. If I differentiate both sides, I shouldn't just get 2x equal to 2s, because we're thinking that x is a function of time and the s is a function of time. So we differentiate x squared, we're going to get 2 times x times dx dt. The derivative of 4d squared is 0, because 40 squared is just 1600, and the derivative of 1600 is 0. And the derivative of s squared should be 2 times s times ds dt. It's just implicit differentiation again, or it's just the chain rule again, really, which are the same thing. Good rule of thumb here is that if you know how something is changing and are trying to find out something else is changing, those things better show up after you've taken the derivative of both sides. If they're not showing up, go back and take a look. Trying to think, there might be one rare exception where one of them doesn't show up, but like it's a rare exception, and I think that's not actually the case. So now that we've got this equation, plug in what you know, solve for what you don't. So we're told that we want to know at the moment the kite is 50 feet away from Julian. So if the kite is 50 feet away from Julian, is that the value of x or the value of s? I think it's actually s, because if we think about if we think about Julian being here, and the kite being here, from Julian to the kite is traveling on this path, which is definitely the path that is labeled by s. So we're going to say that s equals 50. And then we know what dx dt is. Dx dt is equal to 10. But we also need to know what x is, right? If we're trying to solve for ds dt, we want to be able to plug in for 50 for s, 10 for dx dt, but we also have to figure out what is going to go in for x. Well, this is a typical Pythagorean situation where you have a 3, 4, 5 triangle, except it's a 30, 40, 50 triangle. So, right, if you know that this side is 40 and this side is 50, you could either use the Pythagorean theorem and say that x squared plus 40 squared equals 50 squared, and solve for x and get 30, or you can know it. And by know I mean, like, if you see that you have a multiple of a 3, 4, 5 triangle, you can be like, oh, well, one side's 40, the hypotenuse is 50, the other side's got to be 30 because they're all just 10 times the 3, 4, 5. But you can also do the math here, right? That's 2,500 minus 1,600 is 900, and the square root of 900 is 30. So that means x is going to be 30, and then we're going to get 2 times 30 is 60. But I wrote 2 times 30 times 10 equals 2 times s, which was 50, times ds dt. So you end up getting 2 times 30 times 10, which is 600, divided by 100, or 6 feet per second, is equal to ds dt. Bonus question. How fast is the angle of elevation from Julian to the kite changing? Before we answer that question, let's think about the answer. So, as the kite moves to the right, is the angle from Julian to the kite getting higher or lower? Lower, definitely. So we'd expect the rate of change of the angle to be positive or negative? Negative, because it's decreasing. So when something is decreasing, its rate of change should be negative. So we're going to find the rate of change of the angle to the kite, and it's going to end up being a negative value because that angle is getting smaller as the kite moves further away. Okay. On the other hand, if it was like a plane flying towards us and we were looking up at it, then our angle of elevation would be increasing as the plane got closer to us. So it's something to think about, because people do ask these questions and it can be easy to get caught up on whether it's a positive or negative rate of change. So sorry, let's draw a little picture again. So we know that this is 40, we know that this is X, we know that this is S, and we know we're concerned with the moment that X is 30 and S is 50. But now we're asking how this angle is changing, which we almost always call theta. It's just, I don't know why theta is the angle name that people have picked to use, but it's definitely the first choice for any angle name that any math person's ever going to use. So we want to know, how is theta changing at the same moment? So now our job is to write an equation relating the thing we want to know, how theta is changing, and the thing we already know, how X is changing. Now I will point out, technically we also know how S is changing, but we know that X is increasing at 10 feet per second at any time, whereas we know that S is increasing at 60 per second only at this one moment. So if they happen to ask us about a different moment in time, we couldn't use the rate of change of S. So it's always safer to use the given things they've given you as opposed to the things you found, unless they want you to do it. So we want to find an equation relating the angle theta and the side X. So which trigonometric function should I use that relates theta and X and preferably not S? There's two good answers here. Say again? Tangent's definitely one of them. What's the other one? Cotangent. Yep. So you can either say tangent of theta equals 40 over X, right? Because tangent is opposite over adjacent. But I actually think the other way is the better way to go. Because if you do it this way and say cotangent theta is equal to X over 40, then when you differentiate both sides, you're not going to have to use the quotient rule. We're going to negative power. In fact, I would even go one step further and say the best choice is to say that 40 times cotangent of theta is equal to X. All these choices are fine, but this is the one that's going to require the least amount of work. So now we're going to differentiate both sides. I hope you're all seeing kind of the steps are always the same, right? We draw the picture, we figure out what's changing, we get an equation relating those things. Immediately after finding the equation, we differentiate both sides, and then right after differentiating both sides, we plug in the things we know to find the things we want to know. It's always those same kinds of steps. So taking the derivative of both sides, with respect to time still, the 40 hangs out. The derivative of cotangent of some stuff is negative cosecant squared of that stuff times the derivative of the inside stuff, which is d theta dt, equal to the derivative of X. Be careful here. I know it's real tempting to just write 1, but the derivative of X isn't 1 here. The derivative of X is dx dt. Again, we're differentiating with respect to time. If it helps, and it might help you, you could make the choice to write this as 40 times cotangent of theta of t equal to X of t, reminding yourself that everything is a function of time. And then when you differentiate, you can say, great, I'm going to have 40 times negative cosecant squared of theta of t, but then I have to multiply by the derivative of theta of t. And then the derivative of X of t is X prime of t. I'm not saying you should do this. I'm just saying if you're having a really hard time remembering that you have to have the d theta dt show up or the dx dt show up, this is one way to help kind of remind yourself of those things. It's not the typical notation, but it's totally fine. All right, we did the thing. We took the derivative, and now we're going to plug in what we know. So we know that dx dt is 10. But we don't know what the angle is. And more importantly, we don't need to know what the angle is. We just need to know that x is 30 at the moment we're interested in, and the s is 50. And cosecant is some side over some side. I never remember. I know that cosecant is the reciprocal of sine, and the sine is the opposite over hypotenuse. So cosecant must be the hypotenuse over the opposite. So cosecant of theta is hypotenuse over opposite. So in this case, I'm going to get 40. Let's put the negative out in front of 40 here. I'm going to get negative 40 times cosecant of theta, which is going to be the hypotenuse over the opposite. So 50 over 40, or 5 over 4, squared times d theta dt. And now we can find d theta dt. So, yeah, we can find it. It's terrible though. So yeah, so d theta dt. Let's divide by negative 40 and get negative 10 over 4 on that side. Over here, we still have the 5 over 4 squared, which is going to be 25 over 16. And then we can multiply both sides by 16 over 25 to get d theta dt is equal to negative 10 over 4 times 16 over 25, which reduces to negative, let's see, you can cancel a 5 here, and a 5 here, and a 4 here, and a 4 here. 2 times 4 is 8, negative 8/5. What are the units on this? Well, better question, what's changing? An angle. So the units should be something like radians per, what am I units time? Second. What about degrees? Could it be degrees? No, cannot be degrees. So when you're answering a question like this, it's always going to be radians per whatever unit of time is. It's kind of weird, but totally kind of fine. Radians are a dimensionless unit, right? They don't have any dimension to them. Because when you're talking about radians, like if you actually think about how we find radians on the unit circle, you're taking the arc length of whatever your angle is and dividing it by the radius. Like, so for example, just as a quick reminder, in a whole circle, let's say my circle has a radius of 3 feet. And the circumference is going to be 2 pi times 3 feet, which is 6 pi feet. And then the way you find the angle, right, the angle theta for 1 full revolution, wow, words, I can write words. 1 full revolution is going to be the arc you go around, which is the whole circumference, 6 pi feet, divided by the radius, which is 3 feet. The feet cancel, and the angle is 2 pi radians. No units really to be spoken of. So it's just kind of funky. For angles measuring in radians, there isn't really a unit. You shouldn't worry about it too much. Like if you're being asked how an angle is changing, you should be like, oh, it's radians per second or minute or whatever unit of time you happen to be using. Don't stress the radians too much. And it was negative, like we thought it was going to be, right? The answer was negative 8/5 radians per second. So it definitely is decreasing. I will point out in the last, no, I still have 2 minutes here, that someone else might phrase this answer as the angle is decreasing at 8/5 radians per second. So they might include the negative sign and say it's changing at negative 8/5 per second, radians per second, or they might say use words to say it's decreasing at 8/5 radians per second. Or you can really terribly say it's increasing at negative 8/5 radians per second, which sounds terrible, but is technically correct. Cool. All right. I hate having 5 minutes left. It's like the wrong amount of time when it comes to related rates. Ish. I know what we can do. So let's talk about one more terrible derivative. I feel like we've done these before, but some people have asked to see a few more, so let's do a few more. Let's say that we wanted to find the derivative of this function, log base 3 of x to the 7th times sine squared of x over the cube root of x to the 5th plus 1 times, what else could, why not? Times, what else could go down here? Let's say, sure, cotangent of x. How lovely. This looks really terrible. I would totally put this question on an exam and not feel bad at all. Because, well, I feel slightly bad that I made it log base 3. I put this question on an exam with natural log, for sure. And I would be happy, if I were a student, I would be happy to have this question. Because it's not hard if we simplify it first. So the whole point of these logarithms of terrible things is to do all of the simplifying before you take the derivative. So before we take the derivative, for differentiating, simplify. As a reminder of the rules we have at our disposal here, the log with any base of a times b is equal to the log of a plus the log of b. The log of a divided by b is the log of a minus the log of b. And finally, the log of a to a power is that power times the log of a. Sorry, that's a real squeezed in over there. I apologize. That's terrible. So those are the logarithm rules we're using to break this apart into 4 different logarithms and then differentiate after we brought down the powers. So step 1, simplify. So f of x we're going to rewrite as log base 3 of x to the 7th times sine squared of x minus log base 3 of the cube root of x to the 5th plus 1 times cotangent of x. And then we're going to break those apart further. We're going to write this as log base 3 of x to the 7th plus log base 3 of sine squared of x minus, now here's where you should be careful here. It's minus all of this, so it's going to be minus 2 things added together. It's going to be minus log base 3 of, I'm going to write this as x to the 5th plus 1 to the 1/3 power plus log base 3 of cotangent of x. I will point out, as I always do for these kind of problems, everything in the numerator is going to end up with a positive logarithm. Every factor in the denominator is going to end up with a negative logarithm or a negative coefficient for the logarithm. Finally, last simplification, bring down all the powers and distribute the minus sign. So we get 7 times log base 3 of x plus 2 times log base 3 of sine of x minus 1/3 times log base 3 of x to the 5th plus 1 minus log base 3 of cotangent of x. We've done all the simplifying. Now we're going to find the derivative. So, a reminder, the derivative of the natural log of x is 1 over x. The derivative of log base 3 of x is 1 over x, and then there's also a natural log of 3 in the denominator. So each of these is going to have a natural log of 3 in the denominator. Yeah. So you're going to get 7 times the derivative of log base 3 of x is 1 over x times natural log of 3. Plus 2 times the derivative of log base 3 of sine of x is going to be 1 over sine of x. There's also a natural log of 3 down there. And then we have to multiply by the derivative of the stuff, which is cosine of x. Minus 1/3 times 1 over the stuff. Toss in the natural log of 3. Multiply by the derivative of the stuff. It's 5x to the 4th. Finally, minus 1 over cotangent of x, natural log of 3, and then multiply by the derivative of cotangent of x, which is negative cosecant squared of x. Still pretty gross, but not nearly as bad as if we had not simplified it first. Yeah. No, I don't want to say that. We'll stop there. 331 is to stop there. All right, that's all I got. I'll see you all on Thursday. Office hours as usual. Not this Thursday, but next Thursday, the 21st. I will not have office hours in the afternoon because I have a meeting I have to go to, but just FYI, and I'll post it on Canvas as well. Thursday, the 21st, I will not have office hours at the regular time. In the afternoon, I'll still have them, no, that's not, no, that's all I have, yeah. Cool, have a lovely day.